This is lesson number 3, properties and changes of matter. We're talking about the properties of matter that can be divided into 2 categories. They can be divided as physical properties or chemical properties. And so we have a dichotomy that's associated with that. So physical properties are able to be observed without changing the identity of a substance. And so you can look at them or you can observe them without having to change the identity or chemically react the substance. So, for example, when you're looking at the color of a substance, right, you're just observing that with your eyes. And so that does not change the identity of the substance. When you're measuring the shape of something or measuring the density, right, you're just putting it through a test, but that test is non-destructive, right? So the opposite of that would be a chemical property. In order to observe a chemical property, you have to try to chemically change the substance. And so that's like combustibility. In order to determine if something is combustible, you have to try to burn it. And once you burn it, you've changed the identity of the substance. Here's an example of that. We have a chemical property of oxidation, right? This is rust forming on iron, and iron readily rusts, whereas chrome-plated steel does not regularly rust, right? It takes a lot longer. So that's a chemical property. Just like when we have chemical properties we're trying to change the identity of the substance, we have to adhere to the law of conservation of matter. So matter cannot be created or destroyed, it can only be changed in form. And so therefore, the law of conservation of mass is true, that the mass of the reactants must add up to equal the mass of the products. And so if you have 32 grams of sulfur and you react it with 56 grams of iron, you're going to get 88 grams of iron sulfide product, right? It's just the way it goes. If you did this reaction and you didn't have the right ratio, you would still have leftover reactants in your product side, right? But it would always add up to whatever you had in the reactant side. So a physical change is a change in which the substance itself, the identity of the substance, does not change, right? Chemical bonds are not broken when they're not formed in physical reactions or physical changes. This is a dichotomous comparison. Again, we have physical changes and then coming attractions, chemical changes, right? But in physical changes, it is generally a change of state or a change in the appearance of a substance. So if you have built a snowman because it's wintertime and you're outside and you're like, I want to build a snowman, and that snowman is subjected to sunlight during the day, it may melt, right? If you're making yourself some hot chocolate because it's cold outside and you are boiling water, that is a physical change, right? You still have water, it's in gaseous form, but now you have also hot water in the liquid form, right? So physical changes, some more examples. We have wax in a candle. So a candle is a combination of chemical changes and physical changes, but the physical change is the wax melting, right? Because most of the time the wax is not burning, it's generally the wick that's burning, which is why it's so slow. And the wax is melting, and so you can actually collect that wax back and reform candles sometimes. And you can see when you're boiling water or when you're cooking on the stove, the steam that is generated, right? Steam will come out of this little hole, but then you have water vapor condensing on top of the lid, and that means it's the liquid that's going back, and it's going to a gas, and then it's going back to the liquid form on the lid of your pot. So a chemical change is when you're changing the identity of a substance. This involves breaking and or forming chemical bonds. Generally, it involves both. You break the bonds of the reactants and you form the bonds of the products. And this is indicated by some temperature changes. You can see this happening when chemical bonds form, that releases energy. When chemical bonds are broken, that requires energy. You can see this through color changes or bubbling or formation of a solid in a liquid. And so let's look at those in a little more detail. The evidence that chemical changes are taking place, there's a large energy change. This energy change is generally visible. Like when you have a combustion reaction, you see the light energy being released in the form of fire. Okay, and the heat energy released in the form of fire. A gas is produced sometimes in a chemical change, and that's usually seen as bubbling. That's bubbling without heating. So if you're boiling water, right, that's a physical change. We just went over that. And a gas is produced, but you're adding heat to it, right? If you have Alka-Seltzer and vinegar that you're mixing together, I'm sorry, baking soda and vinegar, it will work with Alka-Seltzer too, but baking soda and vinegar and you're mixing them together, that's releasing a gas, but you didn't heat it, right? And number three, a precipitate forms. A precipitate is what you are seeing in this illustration over here. So this is a precipitate, probably lead iodide, that is being formed in the solution, and that's a solid that forms from a combination of two solutions. So here's a colorless solution here. There was a colorless solution here before you added the solution, or this before you combine the solutions together. Okay, or a permanent change in color, like it's changed the identity of the substance. Okay, and so one of these is always present for a chemical change, but sometimes you see them also in physical changes, right? Like if you add food coloring to water, it looks like there's a permanent color change there, right? But it's just that the color of the food coloring is being added to the water, right? It's just being dissolved in that. So here's another example, a couple examples of chemical changes. So this is from the first day demo, penny demo. It's not really, but it's exactly like what we saw, right? You have the blue solution of the copper nitrate, and you have a little bit of a green solution on the top and the red-brown nitrogen dioxide gas up there. And so those are different than the products that you start, or than the reactants you started with, right? You started with copper and nitric acid, and now you don't have copper and nitric acid anymore. You have different products produced. In combustion, if you're combusting a match, right, in the match here, there's cellulose, right? That's wood, and that is being combined with oxygen, and then it's forming carbon dioxide and water vapor that are flying away, and you're left with less match afterwards because the cellulose was converted into carbon dioxide and water. Okay, and there's some other examples here: cooking meat, bananas turning brown. So it's all about the reaction. It's all about the chemical equations. So when you write a chemical equation for a reaction, you can determine if it's a chemical change or a physical change. So in this example, I'm burning methane in the first one. And so you have CH4, which is methane, plus O2, which is oxygen, and that produces carbon dioxide and water, right? And carbon dioxide and water are different. They're different chemicals than you started with, than the methane and the oxygen. And that's the indicator that it's a chemical change, because you have changed the identity of the chemicals involved in the process. Whereas if you're boiling water in the example at the bottom, right, you have H2O as a liquid and it's going to H2O as a gas. Well, it's still H2O, right? It's the same thing, but it's just in a different state. So it has physically changed, but it has not. The identity of the substance has not changed. Okay, so I hope that helps, and I hope you're able to fill in all the blanks.